Hello again, my dear students. Now it's part number 4, which is the last part for our BJT or bipolar junction transistor working as an AC amplifier. As I mentioned in the part number 3, we are going now to solve two basic amplifier circuits. The first we will call it the common amplifier, the common emitter amplifier. Let's first start with drawing the complete circuit of this transistor. As you can see here, we have our NBN transistor, and we know that it's NBN because the current direction of the current is going into the emitter. Now, for the emitter terminal is connected to a current source and then to a negative DC supply. We call it negative VEE. And now and here also we have a capacitor like that. In the collector terminal, you have first a capacitor, and then you have the RL or the load resistance, and this is the indication for the output. And also you have another RC resistance connected to VCC, which is another DC supply. What about the base? For the base, we have a resistance like that called R capital B, and also we have a capacitor connecting the input but through a resistance. So this is the input VE, V swing, connected here to the ground, and this is a resistance which is called R swing. Now, please remember that this capacitor and this capacitor are called the coupling capacitor. Here, this is to couple the input to the circuit, and this is to couple the output to the load. We put these capacitors to get rid from any DC value, as we mentioned in the MOSFET and as we mentioned also in part number 3 in this lecture. So if you have here an DC current or a DC voltage, this DC current and DC voltage will not pass to the load due to this capacitor, and again here. Now, what about this capacitor? This capacitor has no effect in the DC because it's an open circuit. However, in the AC, this will be somehow short circuit, so this DC biasing will disappear. You will not have a current and you will not have a DC supply because this is now somehow a short circuit. So the effect of this capacitor appears only in the AC signal, in the AC circuit, when you make a short circuit to this biasing. If you remember, in the MOSFET lecture, I told you that whenever you have an AC MOSFET, you have to make first a DC analysis and then an AC analysis, because the AC analysis was dependent on the DC analysis. If you remember, we calculate the VGS, the VDS, the ID, and we plot the load line and detect the operating point. And these values help us in order to calculate the GM, which is the transconductance term in the MOSFET circuits. However, in the BJT circuits, we will not need to do this. We will go directly to the AC. And during solving the problem, you will know why we don't need to make an DC analysis. We have all the time to assume that this transistor or this circuit is working in the active mode. And I will state this in the body of the question, that please assume that this BJT is working in the active mode. So you don't need to investigate the DC analysis. And we will know after maybe a few minutes, you will know why we will not need to make it. Now we need to make an AC analysis. In order to make an AC analysis, we need to replace this transistor by either the bi model or the T model. Now in this part, I will solve two problems. I will first start by solving the first problem using the BI model and the coming problem with the T model to show you how we can use both models in order to make our analysis for the AC signal. Now let's start by solving using the BI model. What we are going to do, my dear students, is that we are going to replace this transistor. Here we have the base, here we have the collector, and here we have the emitter. And we are going to replace this transistor by the BI model. If you remember, the BI model was look like that. Here you have the base, and you have a resistance which called R BI, and then you have an emitter, and then you have a voltage dependent current source which called GM times VPE, where VPE is the voltage drop here on the BI resistance, on the R BI resistance, and of course this is a collector. So this is the small circuit model for the BJT, why we are using the BI model. What we are going to do now is that we will put this model here in this circuit, and we will start to solve the circuit based on that. So let's first, I will make the paper like that in order to use maximum area of the page. Let's first start with the transistor itself. I will start to replot what I did. This is the base, this is R BI, and here we have the current dependent voltage source, and this is the collector. And of course, this is the emitter, and the current flowing here equals to GM times VPE, where this is VP. Okay, so this is a transistor. This is basically the transistor. Now, let's start to connect these three terminals with the circuit. Let's, for example, start with the easiest one, which is the emitter. Now, the emitter is connected like that. However, as I previously mentioned, this capacitor is treated as a short circuit in AC. So if here we have a short circuit, that means now we short circuit over that, and the emitter is directly connected to the ground. So we can simply connect the emitter to the ground. Very easy like that. Okay, this is the first. Now let's go to the base. First, we have a resistance connected to the ground. So we have a resistance like that. So this is called R capital B, as you can see. Then we have a capacitor, which we will treat it as a short circuit, and then we have an R swing and an AC source. So it's R swing, and this is the input, which is B swing. So now this is the circuit. The emitter is connected to the ground. The base is connected to a resistance R capital B, as you can see, and it's now connected to R swings and then the supply. What about the collector? Okay, first the collector. Now again, it's a capacitor. So the capacitor is a short circuit. So this is a wire, and then we have an R load to the ground. So now we have R load to the ground. And also, here we have collector point connected to RC and then VCC. But please remember that this VCC is a DC supply. Now we are doing an AC analysis, so we are deactivating all DC supplies. So while you are deactivating the VCC, this will be connected to the ground. So simply RC will be connected to the ground. It is again typically what we did in the MOSFET. So we have our RC like that. So this is our circuit now. We have the emitter to the ground. We have the base to R capital B and R swing and V swing, and we have the collector connected here. Please remember that sometimes you may have an output resistance here, which, if you remember, indicate the output resistance of the MOSFET in the active region, where you have this tilting or this slope effect, if you remember from the MOSFET and the BJT. So sometimes you may have an output resistance here, which will not actually make it different in the solution by all this. Okay, so this is the configuration. Now, what is required from me? What should I do? Here we have three basic requirements. You have to calculate the input impedance or the input resistance, the output resistance, and the gain. Let's start with the input resistance. If you examine the question in the slides, you will find that there is an arrow here. Let me draw it, indicating that this is a place where you should calculate the input resistance, because basically what is on the left-hand side of the capacitor is the input. So we are calculating the resistance just after the input, as you can see here. So let's now repeat this arrow in the small circuit model. So in this way. So now this is the indication for the input resistance. What is the input resistance? As you can see, simply you have two resistance in parallel. You have the R capital B resistance and, you have the R capital B resistance and you have the R pi resistance. These are the two resistors in parallel. So R in, or the input resistance, is simply the RP parallel with R pi. So this is simply the input resistance. RB will be given, and R pi is equals to beta over GM. Okay, beta will be given in the body of the question. GM will be calculated in few seconds. Please wait. So this is the R in, or the input resistance. What about the output resistance? Okay, the output resistance, you will find also another arrow. If you examine the slides right now, you will find another arrow in this direction, which indicates that, okay, we need to calculate the resistance from here. So let's now repeat it. It should be, this should be RC and this should be RL, and then I can make the arrow here. I'm sorry. So as you can see, this is the direction. While you are calculating the resistance, you are deactivating the current sources, of course. So what you are seeing here is just the RL. So our output is equals to, sorry, RC, not RL. What you are seeing here is RC, because as you can see from the question, the indication is on the left-hand side of RL. So RL is not included, so just it's RC. Okay, so this is the input resistance and this is the output resistance. What about the gain? The gain, as I mentioned, is equals to V out over V in. Very simple like that. So what is V in? V in is a V swing. What is V out? V out is what the voltage I got here. I got in this point. This is the output voltage, if you remember. This is the V out. So let's start with the easiest part. This is the V out. What is the voltage here? Yeah, if you examine this circuit, you will find that you have a current source. This current source is feeding to resistance, which is RC and RL. RC and RL are parallel. So basically, the voltage drop here is the resistance in parallel multiplied by the current. But as you can see, that the direction is the current is coming from downward to upward. This is the direction. So it's negative to the direction of the voltage. So V out equals to negative the current, which is GM multiplied by VBE multiplied by the two resistance in parallel, which is RC parallel to RL. This is simply the output current. But GM is a transconductance constant, which is IC over VT. We will calculate it later. But what about VPE? What is VPE? VPE is the voltage drop here, the voltage drop on the R pi resistance. How can we calculate the voltage drop on the R pi resistance? So we need this point. We need the voltage drop here, because the voltage drop on the R pi resistance is the same like the voltage drop on the R capital B resistance. They are parallel resistance. So what is the voltage here? Let's see. We have a voltage input, which is V swing, and then we have one resistance, R swing, and two resistance in parallel. So it's very simple. It's a voltage divider equation. So VPE equals to the input voltage, which is V swing, multiplied by the voltage drop, the resistance across the voltage drop, which is RB parallel to R by, over which is over the summation of all resistance, which is R swing plus RB parallel to R pi. So it's simple like that. So it's the output voltage equal to the input voltage multiplied by the second resistance R2, which is now it's the parallel combination of RB and R pi, over the summation, which is R swing plus RB parallel with R pi. So this is the overall equation. Then you can substitute by this VPE here. So V output equals to minus GM times, I will remove VPE and write the term there, which is V swing multiplied by RP parallel with R pi over RP parallel with R pi plus R swing. All these terms is still multiplied by RC parallel with RL. As you can see, this is the input and this is the output. So the gain is the output over the input. So simply the gain, which is V output over V input, is minus GM multiplied by all these terms, except of course this V swing, which is the input. So I will make this here as the denominator, which is the gain, and then this is the gain term. So this is the complete solution for the first amplifier. You will have it the same, but with numbers maybe. So I'm just here solve it symbolic in order to understand the concept. However, you can easily substitute by numbers whenever you need. Now, in the next part, I will go to the second example. Thank you very much.